cutie patootie math angel. Welcome back. This is Decaf-Math ASMR. I hope that you're doing well today or tonight. I wanted to invite you to join me here in our little math nook and just take some time to relax, and just hang out. I hope that you find it comforting and peaceful, and there's just no pressure or anything here. But if you wanted some company as you work on some homework or just something boring to tune out to as you drift off to sleep, I hope that this blesses you in some way. But I'm just going to chat about a cute little question. It's a basic little integral from probably a first calculus class, and I don't have anything planned other than to chat about the problem, so I thought we could just hang out and chat. But what I like about this question is that it's a simple integral, like I said. So if you've taken calculus, you could probably do this in your head. But we're going to take some time to solve it two different ways. The first is going to be based on just the simple concept of the integral being like an antiderivative, the opposite of a derivative. And so we're going to just take time, not just memorize the rule, but we're going to take some time to build some intuition behind that. And the other way is to do it geometrically. So there's going to be a little bit of something for our geometry friends and pre-algebra and algebra friends here. So I thought that was cute. But as always, there's no pressure to pay attention or anything. Just do what you feel like. It's all okay. I'm just grateful that you're here in our little math nook, and let us just relax, and maybe catch a tingle or two along the way as well. Yeah? So, needless to say, this isn't a formal lesson or anything. So, let's get to it. So the integral itself that we're looking at is going to be a definite integral. So let's break that up. So we have, that's our integral sign, and we're just going to integrate x, the function f of x equals x, with respect to x. That's it. And it's going to be a definite integral, meaning we're going to have a lower and upper bound. They're going to be constants today. So I'm just going to go from 2 to 5. From 2 to 5. So the integral of x with respect to x from 2 to 5. Okay. So just as a general overview, in a first calculus class, you often start with the derivative, and we can start with a limit definition of a derivative, and then we start to build some rules for calculating it, and we have an interpretation. We're talking about slopes of a tangent line or the tangent line at particular points. So we spend the first half of a calculus class chatting about derivatives, and then we move on to integrals, which we can start to think of as anti-derivatives, the backwards of that. And at first it kind of seems random, I think, to go from like a derivative to an integral, but it all comes together in our fundamental theorem of calculus, which is like often introduced right at the very end. It ties everything together so beautifully. But when we first learn about the integral, we might start with some Riemann sums. So again, there is a visual interpretation of what this means, similar to the idea of the slope of a tangent line. We have a visual for the derivative. We also have a visual for the integral, and it's basically an infinite sum, and we can do more of that here on this channel, but just as a little general idea here, we do have parallels. And so as far as calculations go, we can use that interpretation with this Riemann sum and finding areas under a curve to calculate what this is. But we can also treat this as an anti-derivative, the backwards of a derivative. So let's start with that way, because I think it's just the most straightforward, calculation-y, kind of boring, but just a straight calculation rule-based way. But instead of just doing this, let's actually build some intuition. So if we consider the integral as being like an anti-derivative, the opposite of a derivative, then let's go in the direction of a derivative first. So let's say we have x cubed. Okay, if I gave you a function f of x equals x cubed, the derivative, the first derivative, so that would just be f prime, or in other words df dx. We're taking the derivative with respect to x, there's only a single variable now, equals 3x squared. So 3x squared. Okay, so let me just write that again. So x cubed. So if I took the derivative, I get 3x squared. So this is one of those rules that we learn when we learn about derivatives. You could do the limit definition and calculate all of that, but that would take forever if you do lots of problems. So it's much easier to just go ahead and learn a power rule, which means that if I take the derivative of a constant, or not a constant, a variable raised to the power of a constant. So that's important. It has to be x to the power of 3, not 3 to the x. Okay, we'd have to do something else with that, but x cubed, the rule says that I take that constant power, move it in front, and then keep that variable, and then do one less. So 3x squared. So in general, x to the n, the derivative of x to the n would be nx to the n minus 1. Okay, so we do have the power rule for derivatives. Okay, and so when we consider an integral as being an antiderivative, we basically go the other way. So if x cubed, if the derivative of x cubed is 3x squared, when I ask for the integral of something, I'm basically thinking the derivative of what gives me this thing that I'm integrating. So in this case, if it's a derivative this way, then the antiderivative, or the integral of 3x squared dx, is x cubed, with a little caveat here, but I need to put in a plus c. So, but you can notice here, if I say, what is the integral of 3x squared? What I'm thinking is the derivative of what gives me 3x squared. That's what the integral is equal to. So if the derivative of x cubed is 3x squared, then the integral of 3x squared is x cubed. And then I need a plus c. So we'll get into that a little bit here too. So technically, x cubed is not the only integral with open bounds like this, any constant here, like x cubed plus 7 or x cubed minus pi or anything else, x cubed plus 10,000, the derivative of that would give me 3x squared anyway, because the derivative of any constant is 0. So it would go away when I take the derivative. So this is actually without bounds here. If it's just an open integral like that, we actually have a class of functions that give us this antiderivative. But in general, it's this concept of going backwards. So derivative going this way, antiderivative going the other way. So in this particular case, the integral of what value or what function, if I'm asking for the integral of x, then I'm basically saying the derivative of what function gives me x. That's what I'm really looking for. So, for starters, I have an x here. So you might notice, let's say, so the derivative of what gives me x. So what you might notice is, let's say I did 2x. Well, the derivative of 2x is 2. So there's no x there. But if I take the derivative of x squared, I get 2x, right? Which has the correct degree here. I have an x, but there's a 2 in front. So we just need to get rid of the 2 somehow. So all we have to do is divide by 2. So if I divide by 2, and I'm allowed to do this because the derivative is linear, so I can take the derivative of x squared over 2, and that would be 1/2 times the derivative of the x squared part, which the 2's cancel, which is nice because that gives us the x. So I'm left with x squared over 2 is the integral of x. And if it were an open integral, I would go ahead and do x squared over 2 plus c, but because we have 2 and 5, we plug in those bounds. So I would do x squared over 2, and then this means to plug in 5 into this, and then minus, and then plug in 2, and that will be our answer. So before we get to actually evaluating that fraction, I thought that we could kind of come up with our very first antiderivative or integral rule just based on what we just talked about. So the derivative of x to the n as a power rule gives us nx to the n minus 1, right? So to do the derivative, that's the derivative, which means if I go the other way, in order to take the integral of x to the power, I kind of want to undo this. So if I do x to the n plus 1, and I take the derivative of x to the n plus 1, and then I do over n plus 1, if I take the derivative of this, that's basically what we did here. This would mean that I put the n plus 1 in front, so it'd be n plus 1 times x to the n plus 1 minus 1 all over n plus 1 because it's a constant. So what that does is it cancels out the n plus 1's, and n plus 1 minus 1 is just n. So that would give me x to the n. So you can kind of come up with this through trial and error, but you might just notice this pattern because we end up adding 1 to the power, to the exponent, so that when we take the derivative and we subtract 1, the plus 1 minus 1 cancels out. And then we divide by the n plus 1 so that when we pull that exponent in front, it cancels out with the n plus 1 on the bottom, so that we're left with just x to the n. So anyway, I think it's cool. So we kind of start to intuitively do it if you have like an x to the power of anything, like the integral of x to the 6th would be x to the 7th over 7, and then plus c if we need the constant part if it's an open integral. But kind of the very first rule, I suppose, unless you do constants, which is the same idea but special case. So the integral of a constant like 2 would be 2x plus c, right? So the integral of a constant c with respect to x, all of this is with single variable, so just x, would be cx, and then I guess in that case plus d, like another constant. So now we have x squared over 2, which again, if you've taken calculus, you probably did the whole question in your head, but building that intuition of an antiderivative can be quite fun. So if you check this in your mind again, you go, what's the derivative of x squared over 2? You pull the 2 in front, so 2x to the 1, but then the 2's cancel, so you have x to the 1, which is just x. So that's how we get this. So then what we do, like we said, is we first pull in the 5, so we get 5 squared over 2 minus, then you put the 2 in, so 2 squared over 2. It's just calculations at this point, so we have 25 over 2 minus 4 over 2. So we have 21 over 2. And you can clean that up if you want to, but that's good to me. It's simplified at least, but you can write that as a mixed number. 10 and a half, but 21 over 2 is good. So that's what I get here. Hopefully the math checks out. So that would be like the first way to do this. So just go ahead and use any antiderivative rules that you know. Okay, so we're going to do this geometrically now, which is really cute. I have to say, not all questions or integrals can be done in this geometric way. This is just a little shortcut. The root of it comes from Riemann sums. So basically, the geometric interpretation of taking an integral is to find the area underneath your curve, your function. And the whole idea of Riemann sums is to add up approximations and get infinitely accurate, which gives you an exact value. But that's not to imply that all integrals can be done in this nice geometric way. If they could, and we could just use geometry to solve integrals, then there's no need for calculus at all. So this is one of the special cases, and we'll talk about that. But what we basically do is graph this function y equals x. So I'm going to just attempt to sketch this here. So we would have x and y, x being our dependent variable, y is our independent. X is our independent and y is our dependent. So make sure you write out your scale. So 1, 2, 3, 4. Positive to the right, negative to the left, positive up, negative down. It's our Cartesian coordinate plane. So I'm just going to graph y equals x. So this might be a little exercise for our pre-algebra and algebra friends here. But basically, I should have a straight line. So y equals x is our basic 45 degree, I guess you could call it that, because the x and the y-axis are 90 degrees. So if you have the perfect diagonal slant there, going from bottom left to top right, that gives you y equals x. So this is y equals x. And so what this integral means is I want to find the area underneath this y equals x, or between y equals x and the x-axis. And if the part of the domain that we're looking at goes below the x-axis, then that integral will be negative. I actually have another video that covers this that you can check out if you are interested. But for today, our domain is from 2 to 5, so it's all positive there. So from 2 to 5. Okay, so I want to find the area between my curve, in this case just a straight line, and the x-axis. So, like I said, in this case, it's a nice, pretty, simple area. Normally, your curve will be, an actual curve, not a straight line. So if you have something like that, and you're trying to find the area under it, that's what calculus is all about. Or, if your function's like woo, you need calculus, because it's not so straightforward here. The area can be done geometrically here, but in general, you can't necessarily do that. So, in this case, when we sketch it out, we end up having a trapezoid, which we can use a formula for, but we can also consider this as two areas, two triangles. So it might be a little hard to see here, but what we can do is find the total area of this outer triangle to the center, to the origin. That triangle minus this triangle gives me this trapezoid. So let's try it that way. So the area in general of a triangle is half times base times height. And so for the big triangle, my base is 5, from 0 to 5, because of this 5. So the base is 5, and so half times 5 times, and then the height is actually also going to be 5, because I'm given the function y equals x. So this point here is going to be 5 comma 5, which means from the origin, I'm going right 5, up 5. So this base will be 5, height will be 5. So half times 5 times 5, which is 25 over 2, which might look familiar. That's the x squared over 2. And then if we do the little one here, the little triangle, to subtract out from this one, I have a 2 across and 2 up. So half times 2 times 2. Because of this 2, I have a little cutout here. So this point would be 2 comma 2, because we have the function y equals x. So if I'm going x to the right, or 2 to the right for x, then I'm going 2 up for y. So I have half times 2 times 2. So that would give me the 4 over 2. And then I have to take the difference. So 25 over 2 minus 4 over 2, which is the same as the x squared over 2, but it still gives me 21 over 2. So either way, whether we just use our standard sort of backwards power rule to calculate it, or if we do this geometrically or graphically, we get the same answer, 21 over 2. So like I said, sometimes the graphically version makes things easier. For instance, if we're trying to find the integral of, let's say, a quarter of a circle or something like that, you have to check your domains, but we already know the area of a circle, so pi r squared. If we want to do like half of a circle or a quarter, we just divide accordingly. But we can get the exact area using our general geometry formulas. But like we said, not all functions can be done in this way. Like sometimes the actual functions are a little more wonky, but you can just use any rule anyway. If you do have like a quarter of a circle, you do end up working with different techniques with integrals that you can still solve using general rules anyway. We just need other tips and tools there. So but in that case, if you happen to notice it as a shape that's familiar and easy to calculate, you might as well just go ahead and get that value without doing all of the integral work. But that's up to you. Just wanted to introduce this cute little idea, even without having to go too much into Riemann sums and all of that here. You can say, even if you're into geometry and algebra, you can even say that you solved your very first integral, just geometrically. So, good fun, cute fun. I hope that it makes sense. Again, this isn't meant to be like a formal lesson or anything. I just think it's cute and nostalgic, and I hope that you enjoyed it. And if you're asleep right now, I'm wishing you sweet, sweet mathy dreams. And if you are interested in any of this, I'd be happy to continue making more videos like this. I do have a calculus playlist going and an algebra playlist going, and I have so many other ideas and so many different random topics to chat about. But thanks for hanging out with me and spending some time here, and I will see you around.